Hello, and thank you for joining Maplesoft's Virtual User Summit. My name is Shola Slough, Technical Communications Specialist at Maplesoft, and I'm your host for this presentation. The presenters for this session are available in the Communication Lounge from 11:30 to 12 p.m. for a live chat on the day of the event. Please head over to the Communication Lounge and select the appropriate scheduled chat for this presentation to ask your questions. If you're viewing a recording at any other time and have questions, please leave your questions on the message board in the Communication Lounge, and a Maplesoft representative will get back to you. This session is titled Maple and Mathematics Research. Maple is an invaluable part of many mathematical research projects. This session highlights the work of two different researchers who explain how they use Maple in their work and which techniques they find to be the most effective. Projects involving the study of self-writing shapes and cryptography will be explored. Let me now introduce our presenters. Dr. Gabor Domokos is a fellow of the Hungarian Academy of Sciences and professor at the Budapest University of Technology. He received his PhD from the Hungarian Academy of Sciences in 1989 in applied mechanics. He was a Fulbright Fellow, later a visiting professor, and is now an adjunct professor at Cornell University, Sibley School of Mechanical and Aerospace Engineering. He was a Korani Fellow at the Institute of Physical Science and Technology, University of Maryland at College Park, and recently was a visiting fellow at Trinity College, Cambridge in the UK. Together with Peter Várkonyi, Dr. Domokos received the Knight's Cross of the Republic of Hungary for inventing the gumbug. William Baldry, professor of mathematics at Appalachian State University in North Carolina, has been a Maple user for over 25 years. Bill has given numerous talks and workshops on using Maple in class and for research. He was co-principal investigator on 3 NSF-funded projects, bringing Maple into math instruction via computer labs, and has co-authored texts based on using Maple in mathematics. The name Maple shows up in his latest book, Introduction to Real Analysis, 12 times, and his favorite syrup is, of course, maple.
Hello, everyone. My name is Gabor Domokos. I'm a professor of mechanics at the Budapest University of Technology and Economics in Budapest. And my giving this presentation joint work with my colleague Peter Várkonyi, who is an associate professor at the same institution. We are delighted to be a guest presenter at the Maplesoft Virtual User Summit, and we are going to present you a summary of a mathematical research where the software Maple played a key role. So the story started sometimes earlier in 1990 when I was a Fulbright Fellow at Cornell University, and I was presented by one of my friends with a rather intriguing question. Most of you are probably familiar with weebles, which are children's toys which would always stand upright if placed on a horizontal surface. A weeble, which you can see now on this slide, has a stable point of equilibrium. This is where it would stand. And on the top of the head, there is an unstable point where you may balance it, but it would not stand stable. The weeble is achieving this behavior by putting some extra weight at the bottom of the weeble. So the distribution of the material is not homogeneous. The mathematical question I was asked is whether it is possible to make an honest weeble, in the sense that we take a homogeneous disk with uniform material density and uniform material distribution, and just the shape of the disk should be of such geometry that it has only one stable balance point and one unstable balance point. So this is a purely geometrical question, and we shortly answered this question in the negative, saying that no such weebles exist in the plane. Some years later, in 1995, I was going to the International Congress on Industrial and Applied Mathematics, which was organized in Hamburg, Germany. And it was a huge congress. 4,000 people were at the congress, and the main plenary talk was given by Vladimir Igorovich Arnold, who was one of the most influential mathematicians of the 20th century. His talk was on various subjects, from mechanics to mathematics, broadly interdisciplinary, but there was a common feature in all topics he described, the number 4. So he proved for various things in various disciplines that some quantity had to be equal or greater than 4. And our previous result about honest weebles in 2 dimensions, planar weebles, means that any 2-dimensional body which is homogeneous needs to have at least 4 balance points, because no weebles exist. That means there have to be at least 2 stable points, which implies 2 unstable points, so the minimal number is 4. And many people, many mathematicians, expected the same result to be true in 3 dimensions. So the result would have been that in 3 dimensions, the minimal number of balance points is also 4. And this would have been a beautiful theorem. However, there was another statement which proved to be even more beautiful, and this was initiated by Arnold. So he suggested in a private conversation that despite the expectation that this theorem about 3-dimensional bodies would be true, he personally believes that objects with just 2 balance points may exist. Now, this was a rather surprising conjecture, and it took a lot of thinking to understand it. First of all, one had to understand why did other people believe that this object did not exist. The mathematics we are using is well in the frame of Greek mathematics. Did the Greeks know about this problem? Did Archimedes know about this problem? And a more general question, is it possible to classify objects based on the number and type of equilibrium points? So these kind of arguments and thoughts lasted for 5 years. So we were thinking about this. What you see now is a matrix, is a table to organize objects based on the number and type of equilibrium points. The rows correspond to the number of stable equilibrium points, the columns to the number of unstable equilibrium points. And as you can see, there are all kinds of objects. For example, in row 6 and column 8, you can see the cube because it has 6 faces where it would stand stable, and it has 8 vertices which serve as unstable balance points. Or you can see here the tetrahedron with 4 faces and 4 vertices. What we could prove, Arnold's question was related whether any object existed in the upper left corner with 1 and 1. What we could prove that if there exists an object in an arbitrary class, say, which is marked now with this red square, one can produce objects to the right and below from these objects. So we gave an algorithm to provide these neighbors to the right and below. This implied that if Arnold's body existed, then all other classes would be non-empty. So it meant that this object is a rather significant object. Is it possible that such an important shape exists, this is somehow a stem cell for all other classes? From the existence of this object, all other classes can be deduced. However, the inverse is not true. It cannot be deduced from the existence of other classes. is it possible that this exists and yet nobody has found it? So we were thinking about this for a couple of years. Finally, we couldn't find this shape, and then I went on holidays with my wife to Greece in 2005, and then I convinced her to look at pebble shapes, and we collected 2,000 pebbles and classified them based on the number and type of equilibrium points. And this is a rather hard test even for a marriage. Finally, we are talking about over 150 kilograms of pebbles. So most of our evenings were dedicated to this exercise. And finally, we had a very large statistical sample. But as you can see in this little table, which is identical to the table which I showed before, we did not find any object which was in any pebble which was in class 1-1. So now there were two possible explanations. The trivial explanation was that Arnold was wrong and such an object doesn't exist. Because if you look at pebble shapes, there are all kinds of different shapes, and you expect to find any type of object among pebbles, but it was not there. So maybe Arnold was wrong. But on the flight home, other ideas came to me, and we started to investigate in a different direction. The flatness and thinness of bodies can be quantified in mathematics, and these values, f and t, are defined to be always greater or equal than 1. For example, the sphere has minimal flatness and minimal thinness, so it is f equals 1, t equals 1. If you take a frisbee, it would be very flat, as our intuition tells us, but the thinness would be approximately 1. It is not thin, but it is very flat. On the other hand, a pencil would not be flat, but it would be very thin. So these mathematical definitions, the formula of which I don't give now, gives values which agrees well with our intuition. And we could prove that if this object, which now I will call the gömbög, because this is the Hungarian name for this body which we assign to it, if it existed, so Arnold's object, if it existed, it would have also flatness and thinness equal to 1 like the sphere, and this would be the only type of object having this property, but it would be not a sphere. So in 2005 we gave a proof of existence, and I will just briefly outline this to show you how we used Maple. So we designed an object in a spherical coordinate system which deviated very slightly from the sphere. So this, in the polar coordinate system, this function was given as 1, which is a sphere, plus a small function which is the difference from the sphere. And we had two free parameters, c and r0. Now, we could construct a function which had one local maximum and one local minimum. However, we had two problems. This object was in general not convex, and the center of gravity was not at the origin of the coordinate system. However, we found that tuning the parameters which we had, we can resolve these problems. In particular, R0 measured the deviation from the sphere. So if we increase R0, then we are getting closer to the sphere. And here we used the Maple 7 at that point. So we are back in 2005. We checked the convexity of the object using Maple 7, and we could identify exactly the region of convexity on the parameter plane. The other parameter c was used to tune the position of the center of gravity. You can see to the left of the red line we have over the origin, to the right of the red line we have under the origin. So the intersection of this line with the convex region gives us a one parameter family of objects which are good, which we call monostatic bodies. Now, this was the analytical proof, but the problem was that the deviation from the sphere was 0.001%. So it is not possible to manufacture this object. And the question is, what is the maximal deviation from the sphere we can achieve? And how can the geometry be achieved? And what is the best available technology? So these are not exactly mathematical questions, but both Peter and me, we are both engineers, and we were thinking about this very hard for 2 years. Finally, we came up with a solution which is deviating from the sphere already by 15%. It's still a monostatic object, and it behaves relatively well under physical circumstances. And this is the shape which became rather well known. Now, did we invent this shape, or did we discover it, or maybe we rediscovered it? That's an interesting question. By looking at the shape, it occurred to us that some tropical turtles have similar shapes. And we went to a lot of research to quantify this resemblance, and we measured many turtle shells. Here what you can see is a gombox shape which was made by an error of 5%, so not a very big error, but as a result it had not one stable point of equilibrium, but at least 16. Much later, I found a shell of a large leopard turtle, and if I placed it on a horizontal surface, I could find many close by equilibrium points. So I realized that this shell is actually an imperfect version of a gombok. Turtles use various techniques to self-right, because if you place them upside down, it's a life-threatening situation for a turtle. So a flat turtle, which you can see on the left-hand side of this slide, is using muscle power, and it's turning over by using its neck and its front legs. Medium turtles cannot self-right on a horizontal surface. However, there are very few, 2 or 3 species, which self-right just by gravity, and these turtles have a shell which is very close to the gombok, so close that the biologists believe that this is not a coincidence, and this we could publish in a biological journal. Now, we made, because we recognize the significance of the shape, we made a series which were numbered, which have individual numbers, and what you can see here is gombok 001, and this we presented to Professor Arnold on the occasion of his 70th birthday on August 20, 2007 in Moscow. And this is the original picture. He was very pleased to see the object, and immediately he gave us further questions to analyze and to answer. The numbered pieces have made a great career. Many institutions have acquired. They are not produced in the order of their serial number, but one number is produced only once. So institutions picked the year of foundation to put the gombok on exhibit, and here you can see some examples. We are very proud that Maplesoft also selected one of these pieces, and Gomboks 1988 was donated by Maplesoft to the University of Waterloo on the occasion of the 25th anniversary of the company. And this was last year, and this initiated our connection with Maplesoft. This concludes the brief story of the gombok. Of course, our current research is not about the gombok, or not just about the gombok. Currently, we are looking into problems of surface evolution, geometrical problems, which are more physical, also three-dimensional geometry related to pebble shape evolution or the shape evolution of asteroids or rocks. These are geometrical problems, and the computations we are doing are very often relying again on Maple, and Maple proved to be a rather reliable companion in this research. I do look forward to receive your questions related to the gombok story or related to our current research. Thank you very much.
Good day. My name is Bill Baldry. I'm a professor of math at Appalachian State University, a school in North Carolina at the northwest corner. And I'd like to talk to you today about Maple as an impetus for a cryptography project. this was a fascinating creature that I've been working on now for several years and trying to get some results. So what happened and how did this start? I was teaching an honors seminar in cryptography. I, of course, wanted to use Maple since I've been using it for a little over 25 years now. And I wrote a Maple package for this honors seminar. The package had all of the standard stuff that I wanted to use in class, the traditional cryptosystems, starting with Caesar system and Vigenère and all the way up through RSA. And then to have some analysis tools, I added a character frequency measuring function, a Kasiski test function that was used along with the Vigenère cipher to look at the distribution of letters. Probabilistic primality testing to test large numbers for primality to use with RSA and such things. And I wanted to implement the newer cryptosystems that just came out, the elliptic curves and Reindel, which we now know as AES, the Advanced Encryption System for the U.S. That was something that my students found fascinating, that the U.S. would actually choose something written by two Belgians, that John van Diemen and Vincent Reimann, and they combined their name to Reindel for the cryptosystem. It's fascinating. It was mathematically very interesting since all the arithmetic is done in Galois field. Now, one day we got going, and we were talking about information entropy, and that the idea is to scatter the information in the cryptosystem so we could see what was happening. Did a little bit of graphics and looked at that to see what was going on, and then one of the students asked about AES and how that worked, and we talked for a while in class, and I went back to my office. Now, I started thinking about the entropy and the key schedule of AES. We hadn't talked about that in class yet. The key schedule is fascinating in itself. You start with an initial key, and that initial key is 128 bits. Then in each round of AES, what happens is that key generates a new key. So we have 10 different keys, one for each round, along with the initial key. The system starts with the key being XORed to the data and finishes so that it's a symmetric operation that makes the decryption much easier. So I went back to my office, and then naturally, what would I grab onto but some Maple to play with the keys and see what happens. Well, I guess we should talk for a second then about what the key schedule looks like. And so to lead up to that, what's AES look like? And it's a 10-round system, at least the version we were studying. Each round uses a standard SFOC substitution. This is a nonlinear function, but it's well known. It's a bijection. It has a very simple formula. So this doesn't really add anything to the cryptosystem. Scrambling letters, but it's a bijection. That's not really going to matter. Then the next operation is a shift row. What we do is arrange all of the data we're encrypting in a matrix. We take the first row, leave it alone. The second row, we shift it right 1. The third row, shift it right 2. The fourth row, shift it right 4. And we end up with a shifted matrix. This, again, is a linear operation. People that study cryptology know that linear is something that this doesn't give any security at all. The Caesar cipher, that's a linear substitution. This one's been broken for a few years now. I remember when they first did it. Let's see. Then the round finishes with this add key. We take the key, that's the part that I want to look at, and we XOR this with it. Now, the key is where we're going to get the nonlinearity. And it's the nonlinearity that's not a very nice bijection. So 128 bits, we do that. This procedure is very nonlinear, and what happens with that is that's going to scatter the bits of the message we're trying to encode. So I looked at this carefully and started to think that the way the key schedule is discovered, or not discovered, but the way the key schedule is generated, this could lead to some patterns. And in cryptography, patterns are bad things. We want to definitely avoid patterns. that helps one break the keys. So questions are, two natural things come up right away. First question, how do you identify patterns in the key schedule? It's one thing to say that there are going to be patterns there because of the structure of it, but it's another to be able to mathematically describe those. This turns out to be a pretty difficult question. Then the second question that's going to be much more interesting in the applied world is, how do you measure a key to indicate the level of the patterns? We want to measure for the keys. We can plug it in very quickly and easily and say, this is going to be a good key. It's not going to have much in the way of patterns. Or this is going to be a bad key. We might see some patterns in there. Now, you might be thinking to yourself, why did I think that there was going to be structure in the key schedule? Well, let's take a look at that. This is the way the keys are generated. If we take the 128 bits along the top row here, that's the key for the nth round, then break that into 4 groups of a couple hex digits there. We've got 4 hex digits in each group. The last group on the right, K12 to K15, we take those, rotate it a little bit, run it through that transformation, which is actually the S box, the substitution box. So that's nonlinear, but it's a bijection. We XOR that with a round key that's just shifting a few bits in it, flipping them back and forth in each round so that it's not the same transformation each time. This we then put into the first 4 hex bits of the key, XOR that, and that gives us the new first 4 bits of the next key. We take those 4 bits, XOR with the previous bits over by 4, drop that down, and you see how this XOR cascades all the way through. So what we've got is on the nth key, the last four hex digits slide across and influence the first 4 of the next row. Then that cascades through. When I was thinking about this to myself, when I heard that phrase cascades through, it was, oh my, there are going to be patterns. Now, one thing that's fun with this, especially in a class, is that all the arithmetic is done in Galois field of 2 to the 8th. This is a very nice structure. Strangely enough, there is a little startup company down in Raleigh, North Carolina, that makes a chip where they have recoded the arithmetic at the chip level to work in the GF 2 to the 8th. That was quite a surprise when I found that at first. So here is an actual key. Let's see. We've got a bunch of 1s and 0s. Along the row there, you see it starts DF, DB. Those are the hex digits for the key. And I look at that, and I see lots and lots of patterns in there. There's some good ones. There's some bad ones. Now, we notice some dots scattered around, but over here, I'm looking now down. I see the mouse over here on columns 104 to 108 roughly. I look at that and I see a big block of zeros. Well, zeros going all the way down through the key schedule. If we're XORing with 0, we're not changing anything. So that one column of 3 that's zeros all the way along doesn't add anything to the cryptosystem. Those bits just fall right through the way they're calculated. Now, from there, slide over 32 bits and down 1 row, and we see that same structure. Here we've got that same big block of zeros. There was an initial line of 1s, but right underneath it, that same big block of zeros. This isn't good. That means that that block is not changing by the key. And the key was the nonlinear portion. That's where we get the security from, is the nonlinear aspect. Everything else is linear. That's easy to crack. Slide over 32 bits again. Now I'm up on the first row, and I see that same form of block up here. I'm looking at the columns 40 to 45. Right there, another big chunk of zeros. If I slide over again towards the beginning, here I am at columns 9 through 12. there's that whole group shifted over and dropped down one row. So it looks like what we're doing is taking a big block, shifting it over 32 bits and down one row, and then repeating that. Shifted over 32, drop down a row, shifted over 32, and drop down a row. That's not good, especially those big chunks of zeros in there. Now looking at the other dimension, if we look across the bottom row, starting at the top lines, we look across the bottom row, we see a big collection of zeros again. And then in the second display, we see another even bigger collection of zeros. Zeros are not good, especially when we have a lot of zeros sequentially. That means things are not changing. And if we're trying to encrypt something, we want the information to disappear. So I'm looking at that, and I'm saying to myself, can I identify these patterns? Well, shift over 32 bits, drop one row. That's going to be hard to codify. So what can we do to find out something? We start looking at that, and, well, ones and zeros, this is pretty hard to see. How about if we just pop up Maple again and say, let's take a look at a graph. This is a random key with its schedule. The key is along the top, and then each row of this, well, you can't see the rows. No, what this is a grayscale matrix plot. Now I look at that plot, and oh my, it's just, there's structure all over the place, and a very defined upper left to lower right flowing. We go hills and valleys. If we start at the upper right, go to the lower left, we see lots of lines that are white lines, and then we can see black lines in there. This is just way too much stuff happening in a pattern to be a good key. This was a random key. So what is it that we're going to do with that random key? Now, I have to come up with some way to measure this. So let's see, what can we think of? If I start looking at the number of zeros and ones in here, that may help. So what we did was tested 1 million randomly generated keys and used this form. We took the infinity norm squared of the key structure, and then not the key structure, change the ones to zeros, the zeros to ones, take the infinity norm of that. Well, what we're doing is we're essentially counting rows of zeros and ones, how many there are in the row, and looking at worst case. Then take a Euclidean norm of those two values, and we get this thing that we'll call a measure of the structure. Well, to do 1 million of these, it took a little bit of work. It was about 34 hours on my old Mac Pro that I just replaced. And the coding, well, we ended up having to dump the keys off into a file as we were generating them, then read the structures back in as matrices, calculate this norm that we've put together, dump that off into the file, and after we got through all of those, then bring it all back, bring all the norms back in and do something with them. So I'm looking at that, and I'm thinking, wow, is this really going to tell us much? This is going to get difficult to prove. What could we do? So let's just take a look at a histograph. And immediately we see a skew normal distribution. When we identified the bad keys in this distribution, they all lie above 4,000. So that says they are all way out on the left. Now, suppose for a second, just think about the number of keys. There's 2 to the 128th different possible keys. If we throw away half of them, so we say half the keys are bad, we're left with 2 to the 127th. This is still not a bad collection of keys to work with. So it's not really a problem if we throw away half of them even. Well, with our outliers being out there above 4,000, we've certainly got a lot more than half of them left. But just taking a look at a specific key, how can we find out? If I back up for a second, here I've got that graph. that graph is really what showed me all the structure. Visually, I could see it going in there. So how can I use Maple to get those quickly? And you say to yourself, can of cake. What we've got here is a nice little maplet. This maplet, we enter the key across this top row, hit the expand key button, and bingo, not only do we see the hex or the decimal, whichever you choose, of the key schedule, we also see the plot. And from this plot, there's a reason I called this one bad key. All of that black in there in the picture, all of that is 0. 0 is tough. Now, compare the picture with the actual matrix. In the picture, you can see a lot more black than you can in the matrix, but remember that each of those pairs of hex digits represents 8 bits. And so when we have something like 3D, well, the 3, there's going to be a couple zeros hiding in that because that encodes 4 bits, and only 2 of them are 1s. So what we end up with then is this maplet that lets us put in a key quickly, generate the schedule quickly, see the plot. We can save it, or we can do some more. The little where it says bad key, this little pop-up, one of the choices there that we used was just a random key. Now, let's back up for a second over to those first 2 pictures. There we are. Looking at those, this one was particularly bad. I had a grad student work on this for a bit, and he was able to identify a set of probably about 30,000 keys that have a structure based on this, that would have blocks that repeat like this. He did it by starting with the maplet, playing with some of the values, then cranking out the key schedules, comparing those and seeing where they changed. If he hadn't had Maple, I think he'd still be working on that. And if I hadn't had Maple, I don't think I'd have even started the project. It just made connecting to the visualization so much easier than anything else. So we get down here. We ran the million of them. We found out that, yep, there is a lot of structure, but it's on the tail ends. There's still the question of how do we identify them? We're still working on coming up with a much more robust function. And so what I'd like to say is thanks for stopping by. And if you'd have any questions, I'd be happy to answer them.
Well, that concludes this session. Thank you for joining us today. And don't forget to visit the Communication Lounge to ask any questions you may have. A recording of today's presentation will be archived, and you'll be notified when it is available.